We are now going to talk about Lenz's law, and I want to start by comparing and contrasting Lenz's law with Faraday's law. You haven't learned Faraday's law yet. Faraday's law is in the next section. However, they go together. Now, you're not ever going to see a test question that says you're not going to see a test question, but you might see a TBL question that's asking you to distinguish between Lenz's law and Faraday's law. The important thing is, of course, that you can do the physics to get to the answer, but it's going to be really hard to talk about doing these problems and how you solve them if you don't know which is which. So very briefly, the one we're doing first is Lenz's law. That is only giving us the direction of induced currents and induced EMF. So we've talked about some situations so far where we have induced currents and induced EMF, and now we're going to talk about even more of them. So Lenz's law gives us the direction. Faraday's law actually gives us the magnitude. So if you want to know in a general situation beyond what we've already talked about, the induced current or the induced EMF, you need both the magnitude and the direction. So in most problems, you're going to be using both Lenz's law and Faraday's law. So that's the distinction. You're going to have both of them together, but it is helpful to be able to talk to others about them, knowing which of these is which. So Lenz's law. First, I'm going to explain it, and then we're going to go through it. This is one of the most challenging concepts to get. There's really no math here. There's not a calculation with Lenz's law. So you should be ready to do this for the TBL quiz because it's purely conceptual. However, there are literally 4 steps to go through, and so it's a little confusing. So the first thing you need to do, right, we're talking about an induced magnetic field. And so, we're talking about an induced current. There's going to be some sort of magnetic field present. You need to figure out the direction of the applied magnetic field. So there's some external magnetic field we're going to be talking about. Figure out what direction it's going. It might be coming from a bar magnet. It might be coming from a coil. It might be coming from a wire or a solenoid or some other shape. Figure out what the direction is. Now then, we're always going to be talking about some sort of loop. So the direction you're figuring out is at the loop, right, in the loop. Because then we need to think about how the flux is changing. And this is going to be the flux in the loop. And again, the previous video went through what flux is. So we always have to have a loop to define flux. So your starting point in the problem is always going to involve external magnetic field, applied magnetic field, whatever you want to call that, and a loop. So figure out what your external magnetic field is, figure out what your loop is, so then you figure out how the flux is changing. Obviously, that means that you need to figure out what your flux is, right, your magnetic flux, but then it's changing in some way, increasing, decreasing, etc. Then, right, so that's the first 2 steps. Then you need to figure out how you're going to oppose the change. And this is the trickiest part. So again, we're going to go through some examples of this. But if you have the magnetic field increasing, if that's what's happening, if your flux is increasing, the direction of the induced magnetic field, right, we're now talking about a second magnetic field, is going to oppose the change. So this is really right here the key part of Lenz's law, step 3. But you have to have the other 3 steps as well. So once you know what your flux is, how it's changing, you want to oppose the change. And so, again, I'll show a picture that goes through this. So you're now creating a new magnetic field that's opposing the change. What that means is if you have an increasing flux, if you have a flux that's getting bigger, that leads to an opposite field. If you have a flux that is decreasing, that leads to an induced field that's in the same direction. If, and this is key, if you have a steady flux, there is no induced magnetic field, which means your current, your induced current also equals 0. And remember, we always want to talk about a change here. Lastly, you're going to use the right-hand rule to figure out the current in order to create your induced field. So 3 is really the tricky part, but you have to appreciate that there's 2 steps to do beforehand and then a final step at the end. So we are going to go through an example. I really encourage you, and after I do the example, I'll probably come back to this. Really make sure you understand this 4-step process. The example we're going to do is pushing a bar magnet towards a current loop, and we want to understand which direction the current is going. So we do our 4-step process, and some of it's already done on this picture. This is a case where you really need to draw lots of good pictures. We know that our magnetic field goes away from the north, right? The second thing you want to make sure you do is understand what loop you're doing. Well, the loop is literally this loop. So this is our surface that we're thinking about the flux through, and we see that the magnetic field there, right, through that surface is down, right? So our flux is such that it's due to a magnetic field down through that surface. Now it's being pushed towards, right? So we've figured out something about the flux. We now need to think about how it's changing. Because it's being pushed towards it, our flux is increasing. Now that doesn't mean it's pointed up. Flux is a scalar quantity. But our flux is increasing because the bar magnet is getting closer to the loop. So our field strength is getting bigger because a bar magnet does not produce a uniform magnetic field. So we know that the magnetic field is down at the loop, but the value of the flux is increasing. So that was the first 2 steps. So now what we need to do is counteract that increase. So our induced magnetic field needs to be the opposite direction. Okay, this is the hard part of step 3. So we need to counteract that, and the induced B would then be this upwards direction. That's going to counteract the increase in flux. That's step 3. So finally then, what current do we need to create that upwards facing magnetic field? A current this way. You use the right-hand rule to figure that out, where this is the right-hand rule where your fingers go around the loop and your thumb tells you the direction of the magnetic field inside the loop. That's the one we use here. So those were the 4 steps. Okay, hopefully that made a little bit of sense. Now let me show you the figure from the book that shows everything at once. So the flux through the loop is increasing as the magnet approaches, and we see that that magnetic field is downwards. That means that the loop must generate an upward pointing magnetic field to oppose the change in flux. The right-hand rule says you get that counterclockwise current. So again, to go back up briefly, get your applied magnetic field, which in that case was due to that bar magnet, that permanent magnet. We've figured out how the flux was changing. It was increasing because the magnet was getting closer. So we said that the field was down at the loop, but increasing. So that means that your induced field pointed opposite, which was up. And so then we use the right-hand rule to figure out what direction the current is in order to get that induced field. So again, please draw pictures when you're solving problems like this. Please label it carefully because we have an induced magnetic field and we have the external magnetic field or the applied magnetic field. And that then there's the relationship between the current induced and your induced field. So there's going to be a second video that goes through a few more examples to hopefully make this clear. But again, this video really was meant to just lay out the steps for you.